Okay, so in this video, I would like to discuss tutorial question. We start with question number 12. Okay, it says here that the rate of heat conduction is 80 kilojoule per hour, area 14 centimeter square, and the temperature gradient is 15 Celsius per meter. Calculate the thermal conductivity of the wall. So basically, in this topic, you only have one formula, and the formula would be Q over T negative K A delta T over L, capital L. So the rate of heat conduction is basically Q over T, kilojoule. So times 10 to the power of 3 change to joule per hour. At a thin wall with an area of 14 centimeters square. So that one is your area A. I changed to SI unit. 14 times 10 negative, supposedly centimeter to meter is -2, but because that one is square, -4. If the temperature gradient across the wall is 15 centimeter, 15 Celsius per meter, that one would be delta T over L. Okay, this one is already in SI unit, so you can use this one straight away. Okay, Q over T is joule per hour. So if you want to find like constant K, you have to change everything to SI unit. So obviously you have to change this one to second. So you can see that this one is per hour. I just write it down here so that you can do a cross multiply. So 1 hour is equals to HOUR over 60, sorry, 1 hour is 60 minutes. So it will be 3,600 seconds. So I got here is Q over T is equals to 222.22. Okay, because this one is Q over T, then the unit will be joule per second. Now substitute back inside the equation there. 22.22 is equals to negative K. We want to find K. Okay, A here is 14 times 10 negative 4, and delta T over L is actually 15, but this one is temperature gradient. You expect it to be negative, so I just put negative over there. So that one is negative as well. Those negative cancel out. So K, now you should get 1058.10, because everything is in SI unit. I can write it down as SI unit. Okay. Question number B. It says that aluminum rod has a diameter of 3 centimeter, thickness of 0.6 meter. One end of the rod is placed in boiling water and another one is in ice. Calculate the quantity of heat transferred through the rod within 1 minute. So basically they want you to find Q. Given it is 1 minute. So you have to find Q over T first and then multiply with the time of 1 minute. Okay, one end of the rod is placed in boiling water means it is 100 degrees Celsius, another one in ice, so 0 degrees Celsius. So I already draw it over here, so I can put it as 100 degrees Celsius and 0 degrees Celsius to indicate one is boiling water, another one is in ice. The diameter D is 3 centimeters, so R is equals to 1.5 times 10 negative 2 meter, and then the thickness is 0.6 meter. Okay, so basically the 0.6 meter is basically the length. Okay, now if you want to solve, did they give you the K? Yes, the conductivity of aluminum is 205. So K is equals to 205. Again, you want to apply the same formula. Q over T is equals to negative K A delta T over L. Okay, but Q over T, you want to find Q over T first and then multiply with the time of 1 minute. Negative 205. Area is pi r square. Okay, this is a rod, so area is circle. Okay, delta T, you have to be careful. Okay, now, before you proceed further, actually you have to draw the direction of heat transfer first. So it will be from hotter region to colder region. So this is the direction. So by right, this one would be my T1 and this is my T2. So it will always be final minus initial. So here will be 0 minus 100. So make sure you draw the direction of heat transfer first, then you don't get confused. So this one is 0.6. I just double check. 0.6 meter, yes. So I got Q over T here. It would be this negative cancel out. So 205 times 5 times 1.5 exponent negative 2 square 100.6. I got here is 24.15. Okay, this one is joule per second. But the question want to find within 1 minute. So Q is basically equals to 24.15 times with 60 seconds. So basically you just bring T to the other side. So I use 1449. And the unit will be in joule. Okay, so next question is question number 13. It says here that X and Y similar length and cross-sectional area. So LX is equals to LY, AX is equals to AY. It's insulated. At steady state, the temperature of the rod is, highlight this one first. X and Y are 140 degrees Celsius respectively at each end as shown in figure 8.5. The thermal conductivity of X is twice the thermal conductivity of Y. So that means my K for X is actually twice than the values of Y. So let's say K for X is K. K for Y, X is twice. So I just put like that. Or else I have to put like fraction. I just double check. X is twice to that of Y. So yeah, calculate the temperature at the junction between X and Y. Okay, so when it says that this is at steady state, basically it means that Q over T is equal for both sides. So that means this one's for X is equal for Y. Okay, and then before you start, you have to draw the direction of heat transfer, which is from hotter to colder region. So immediately I can put this one as T1, T2 and T3, and then I substitute Q over T. So it will be negative K A dt delta T, delta T over L. This one is for X. Negative K A delta T over L. This one will be for Y. L and A is the same, so cancel out. K on left hand side is for X, which is negative as well, cancel out. So it will be 2K over here and K over there. Okay, delta T here will be T final minus T initial. So for this part, it will be T2 minus T1. And then for this part, you can see that flow from here to here. Final is T3, initial is T2. So it will be T3 minus T2. Obviously, you have the values for T1 and T3. You can substitute inside. So the value for T1 and T3, so cancel out the K first. T1 is 100, T3 is 40, and T2 you want to find. So it will be 2T2 minus 200 equals to 40 minus T2. I bring T2 to one side, to the left hand side. So I will get 3T, T2 equals to 240. So T2 is equals to 80 Celsius. Okay, next question, question 14. Two properly insulated uniform rod D and E make thermal contact at one end as shown figure 8.6. Cross-sectional area are the same, so A for D is equals to A for E. The rods are in steady condition. Determine the temperature gradient around rod D. So they want to find the temperature gradient for rod D. Again, just draw the direction of heat flow. It will be from hotter to colder region. So it will be like that. Okay. And then temperature gradient is equals to delta T over L. So it will be T final minus T initial. So label this one T1, T2, T3 based on the flow. Final will be over here, initial will be over there. So it will be T2 minus T1 divided by the length of D. So it will be 80 minus 100, 0.2. So temperature gradient will always be negative, because it always flow from hotter to colder region. 80 minus 100 divided by 0.2. But here is negative 100. Unit will be Celsius per meter. And B, calculate the temperature T at the free end of rod E. We can do a new page. So this one is actually already in steady condition. So when it's at steady condition, you can say that Q over T is equals to Q over T, which is for D equals to at E. And then just continue similar with the previous question. Negative K A delta T over L, this one for D. And then negative K A delta T over L, and this one for E. Okay. Areas are the same for both. Cancel out. Negative can cancel out. Is K is given? Yes, K is given. One is K, another one is 2 over 3 K. So KD is over here. K. Just double check. 2 over 3K is over here. Delta T will be T final minus T initial. So again, T2 minus T1. And for this one, it will be T3 minus T2. But I think delta T over L, we already calculate. So that one will be negative 100. And this one will be T3 minus T2. And the length is 40 centimeter, 0.4. K can cancel out. So negative 100 divided by 2 over 3. I should get 150. T3 we want to find. T2 is 80. So your T3 is negative 60 plus 80 will be 20 Celsius. Now actually they ask you to sketch and label graph as well for variation of temperature with a distance x along D and E. Okay, so that one's part C. So basically you have to draw the axis first. It will be temperature against distance. So you already use SI unit, so I just put there in the first place. Then you have 3 different temperature just now. Maybe this one, I mean, you don't actually have to use equal scale, roughly support that is okay. Okay, 20, 80 and 100. So the three temperature T1, T2, T3. And then the length here is the length of the first material 0.2, and then the second one is 0.4. So 0.2 plus 0.4 will be 0.6. Okay, the length here is 0.4. Again, just bring it to the left a little bit. So this one is at position 0.2 is 80, and then the last one is over here. Okay, so if you want to draw the dotted line, you can draw it like this. Okay, but the actual one that you have to draw is this one. This is the temperature gradient. Oops. Okay.
She says that she loves